Okay, guys, welcome back. So we need to have another discussion on an attachment that we can connect to our GC system. All right. So we've already talked about a few maybe different types of detectors, but the problem here is that these detectors are on the back end of the actual instrument. All right. And we need to talk about some of the attachments that happen on the front end of the instrument. And we really already have done this with the headspace unit that we've talked about. But in this video, and maybe in the couple of others that will follow this, is going to be something called the Purge Entrap system. So we need to talk about the purpose of the Purge Entrap system. Why is it important? How does it work? Why does it work? Why would we want to use one in a laboratory? And maybe compare that to the headspace unit that might be in the lab as well. Because listen, they can't do the same job, because if they did the same job, one would not exist because it would condense it down into one type of attachment. So headspace is different than Purge and Trap, and we need to here talk about the difference of Purge and Trap and why someone would want to use it. All right, so this is an attachment that goes onto typically a GC unit, and this Purge and Trap does something pretty special. And the very first thing that it does is that it purges. Well, go figure, who would have ever guessed? And then the second thing that it does, it traps. Well, now how much more difficult can this get? This Purge and Trap system will purge something and it will trap something before it goes into my GC instrument. All right, so of course it's going to be a little bit more complicated than this. So we need to start looking at the details here. All right, so let's say that I have a sample, and I put this sample into a closed container with a lid, and I've got some liquid into this sample. And this sample, depending on what it's made of, could do two things. All right? No matter what happens on the inside, something is going to happen. Does that really even make sense? I don't think that it does. So let me rephrase this for a second. I have a sample into a vial, and that sample can do something. One of those things, option number one, is if this is a volatile sample, which means that it evaporates very easily, this stuff could start evaporating and it could start filling up the empty space above the liquid. All right, so this is great. And we kind of already talked about this. This is headspace. That's the term that we use for this area up here at the very top. And that's the purpose of the headspace analyzer that we can put on the GC instrument. All right, well, that's one option. But here's the problem. What if we bring a sample into the laboratory that's still a liquid, and what we want to measure is in a lower concentration? Super low. Well, if this is volatile, there's nothing different that's going to happen. It's going to evaporate, and it's going to go in the headspace. But because this concentration is lower, the concentration in the headspace is also lower. Okay, so this is the headspace traditionally that I have talked about already. And if this is more of a concentrated sample, there's more concentrated component up in the headspace. And this headspace goes into the GC system, and that GC system sees that component because it's sensitive enough to see it. But here's the problem. Sometimes in the lab, if I have a very weak concentration, that will give rise to a very weak sample in the headspace. That very weak sample in the headspace would go into the GC, and then we have a detector on the end, and the problem is that it cannot detect it because the concentration is too low. So there's two routes here. One route is if I have a concentrated sample that gets analyzed, that concentrated sample goes into the headspace like we've talked about before, and the instrument can see that because there's enough of it there to see. But if I get a really super low concentration of stuff that gets submitted to a lab, and I'm relying on the headspace to have enough sample in it to be seen by the detector, there is a chance that not enough will be in that headspace. I run it through the GC. The GC cannot see it because it's too low, and I make the assumption that it's not there, when in actuality it is. This is the purpose for the Purge Entrap. So the Purge Entrap system is used for very low concentration work. And it really has to be given to volatile organic components or compounds. Things that will evaporate off very easily, things with pretty low boiling points, things that I can heat up just slightly and start evaporating those off. As long as that can happen, this is a suitable candidate for Purge Entrap. If it cannot happen, I'm going to have to think of another way to analyze those components. All right, so for example, one of those things would be, of course, something like acetone, right? Acetone has a very low boiling point. Acetone evaporates off very easily. And if I put acetone into some water, I can put very small amounts of it there. And I can run this mix on a Purge Entrap system. And the Purge Entrap would purge the acetone out of the sample. It would trap the acetone, and then it would analyze the acetone that it caught. So here's a picture of our Purge Entrap system. Now, just like many of the instruments out there, there's different manufacturers, there are different makes, there's different models, and even Teledyne Tecmar, which is the manufacturer of our system, has a newer and improved model that is out there now. So ours is basically junk. But I'm not going to say that because it still does its job. But Teledyne Tecmar has moved on to bigger and better units that they claim are more user-friendly and more reliable than the Stratum model that we have. So Teledyne Tecmar you're seeing on the screen, their name is here to the left. That is the company's name that makes this Purge Entrap unit. And if you go to their products, this is actually in their discontinued products. They no longer make it, of course, and you will see this Stratum that is listed as one of those instruments. The Stratum is the Purge Entrap unit that we have, so if you come into our laboratory one day, or maybe you're getting ready to do the lab on the Purge Entrap system, you're going to see this model that looks like this to the right-hand side. Very simple, very small as far as footprint goes. There's not a lot to this instrument, but for some reason Teledyne Tecmar thought that they needed to make it better. So they claim that they have, and who knows if they really have or not. That could be a lie just to get more money from a laboratory, and that's probably the case. But you're seeing applications in industries here. So up underneath, all Purge Entrap units, no matter what they are, can find their home in environmental. And they list this one as number 1, okay? The environmental industry is really probably the most common industry or lab that uses Purge Entrap technology. And the reason is because we're looking for those environmental contaminants. And those contaminants could be very highly carcinogenic compounds, herbicides, pesticides, who knows, but they are there in low concentrations, and we need to figure out if they're present or not. Because maybe part per billion levels could be enough to cause some health defects or effects in someone if they're not careful. Food and beverage is also listed there. Forensics and toxicology, pharmaceutical, petrochemical. You really could find Purge Entrap in any of those fields, but by far the most common is the environmental side of the house. So, an environmental lab, Very common. You might see a Purge Entrap system. If not, the Purge Entrap system could probably make your life a little bit better. If you're not in the environmental world, don't sweat it though, because there could still be uses of Purge Entrap that's out there in any of those other fields that are there. Okay? So this is the piece that we're getting ready to talk about, and we're going to kind of explain to you how this whole system begins to work. So we know low concentration work. This low concentration will evaporate just like all the others. The problem is that this headspace will be also low concentration, and we need to go through and kind of beef that up a little bit so that our instrument can see it. All right, so this is what happens in the Purge Entrap system. So let's say I take a vial, and this vial has some sample in it. I'm just going to kind of take the vial, fill it to the top, and let's say that this is a water sample. Keep in mind, water is a no-no, especially in the world of GC. I should not be injecting water directly on the instrument. So, because of that, I need to come up with a way that I can get rid of this water. Right? I need to get rid of the water. I need to make sure that it doesn't get injected on the GC, but I need all the stuff in that water to be injected on the GC. So that's going to be the purpose of the purge side of the house on the Purge Entrap system. So what happens is that this auto sampler needle or some type of injection port will basically puncture the vial, and it would suck sample up into what we would call a sparger tube. So the sparger tube. Some people would call this a U-tube instead, because that's basically what it looks like. It looks like basically a piece of curvatured glass that makes a U, and these get basically attached to the top of the instrument up here on the very top. So this sample will go into this U-tube or the sparger tube, and it would fill this sparger tube up. So now all of my sample is going to be in here ready for the purge to take place. Have you ever watched that movie? If not, I probably wouldn't encourage it if you have a weak stomach. All right, so there's my sample. It's in the sparger tube. It's ready to be purged. Okay, so what happens is that on one side of this sparger tube, I have another line, and this line is basically from the gas. And this gas is typically helium, and the reason is because helium is used for most gas chromatograph instruments, and to make it easy, they have basically made this model to accept helium gas as well. And the helium purpose is to do the purge. So what happens is that it basically blows bubbles through your sample, and it begins to purge all of those volatile organics up and out of your aqueous environment. Okay, so the way that I like to explain this is, imagine that you have a soda in front of you and you have a straw that goes down into that soda, and you put your mouth on one end and you begin to blow on one end of it. What you would see is bubbles would happen from the bottom of that straw, and those bubbles would basically go through the entire soda sample and then eventually up and out. If you blow enough, and if you blow long enough, what would happen is that your air from your mouth would basically blow all of that carbon dioxide out of the soda, and that soda would go flat. And the reason is because you are pumping it full of the air from your mouth. So you're taking up all the room and you're pushing out all of that stuff, right? The same thing is happening here in the sparger tube. So we have helium that goes into this U-tube shape, and that helium is getting pumped through the sample. And this is bubble, 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 bubble. All of those helium bubbles are traveling through this sample, and what it's doing is that it's beginning to push out all of the volatile chemicals on one end of the U-tube. everything's getting bullied, and it's getting bullied by the helium. Well, this kind of happens naturally in a way. All right, so for instance, when I say that, let's say that we do not have a purge system and we have some sample. We know that some of that sample will go up here in the headspace. But if I don't do anything to it, it's going to get to a certain point where it comes to equilibrium. That means that no more will go into the headspace. If I have a really weak solution, then no more will go into the headspace, and I have a really weak concentration in the headspace. Well, if I could somehow maybe suck it up off the top and get rid of it, in the next step, I could get more of this solvent because it's no longer at equilibrium now, right? I could get more of this chemical to evaporate and go into the headspace. And then I could maybe come back through a second time and skim it off the top, disturb the equilibrium balance, and more of it will evaporate off. And I could keep skimming off the top, little bits by little bits by little bits, as long as I collect it into a separate container. And then maybe I could have enough of it that has volatilized out of the sample that I can then analyze. That's exactly what's going on here. All right. But this machine is doing it more in an automated process, so I do not have to worry about it. So helium goes through, it bubbles, it pushes all of this stuff out, it continues to bubble, which means it continues to remove these components from the sample, and as long as it's leaving the sample is going to continue to volatilize, it's going to continue to evaporate, it's going to continue to leave that aqueous solution, and as long as I'm capturing it somewhere, I'm not losing any of my sample. So it's going to be pretty important to make sure that you take a look at your helium line. Make sure that the helium tank is full. Make sure that your helium tank is not getting empty, because if the helium is not supplied to the purge system, the purge cannot do its job. All right, so that's the number one problem that people begin to have. Well, this also requires some hookups. This glass tubing is also connected using a nut, almost like a GC fitting, and you want to make sure that that is leak tight. You do not want leaks to happen in this area because that will lose your sample. Over here on this side, that also has a nut, so you want to make sure that that is pretty tight. You don't want to lose sample from that end either. And then on the back side of the instrument where the helium comes in, if it comes in from a different place, you also want to check those connectors as well, though those leaks will begin to cause a problem. So this is the first half of the purge system, and that's really all that it's doing. It's taking some of your sample in an aqueous environment that cannot be injected on a GC because it is water, and it's delivering it to this sparger tube, and helium is coming in, and it's basically getting blown through the sample. And that helium is getting bubbled through. That helium is pushing out all of the volatiles, and all of those volatiles are beginning to leave the water sample. Well, they have to go somewhere, and where they go is on the inside of the instrument. You really cannot see this area unless you take the cover off, with our model at least. And where this decides to go is basically a column. I'm going to draw it as a column. It might not be the same type of column that you're thinking of if you did some other like lycopene labs or some chromatography labs so far, but you can think of it as a column. And all of these volatile organics are eventually going to go on this column, and they go in here, every single one of them, and they begin to load the column up. All right, so this is the part where the trap happens. So purge is happening here, and a trap is happening here. So this column receives the volatile organics, or VOCs, and it will trap those VOCs there, and they will not go anywhere. So during the purge event, which is what's happening here, during that purge event, these components are continuously getting loaded onto that column. And they will keep loading onto that column. And they will keep loading onto that column until the purge is over. So first off, you're going to have to be really careful with the time here. You want to make sure that you give that sample enough time to purge. And this typically is about an 11-minute purge time. This can be a little bit longer or it can be a little bit shorter. That just really depends on the method that you're doing. But quite honestly, most of the time that I've seen a purge and trap method, it's always been 10 to 15 minutes of purge, with 11 being the most common. So 11 minutes of helium bubbles just continue to go through that sample. And for that 11 minutes, the VOCs are leaving the sample and they're getting trapped onto this column that's on the inside of the purge and trap system. Eventually, what will happen is that the purge will stop. So the purge stops, no more helium gets bubbled through. We're going to assume that all of the volatile organics are out, and all of those volatile organics are now trapped onto the column. And that's where I'm going to stop this video. So in the next video, we're going to talk about what happens in the next process. What happens now that they are trapped? How do they eventually get to the GC instrument? So stay tuned, come back. I know that you're having a ball and a blast listening to Purge and Trap Theory here. So come back, get it over with, take some more notes, and you'll be on your way for another A.